Hello. We're going to continue now with our lecture about heat flow. And we've already discussed the leapfrog method, time stepping. And we said that it's good, but there is a more powerful method, and that's this Crank-Nickelson method. So it's also a leapfrog method. It's an improved leapfrog method. So it's a method in which we take present time solution and generate future from that. But it's higher precision, but you pay a price. It's more complicated. But it has some interesting mathematics. So this lecture will be more on just the algorithm development and a very good example of how you can improve algorithms and how you go about doing it, and then the price you pay. It's not always a bad price. It doesn't necessarily slow you down even. So here's our problem again. We have a bar. Starts off initially, time t equals 0 at 100 degrees centigrade. The ends are always kept at 0 degrees in ice water, and the length of the bar is insulated. So no heat flows outside the bar other than through the ends. It's aluminum, so we know what the value of the constants are, and it's isolated, and the solution asks for what is the time dependence of the temperature for each point along the bar. X will be the position along the bar. How does that temperature vary with time? Okay. So the problem we had with the ordinary leapfrog method, as you recall, is that the time derivative, dt, d with respect to t, partial derivative, we had to use a forward difference method, and that's not very accurate. If we could change that to a central difference, where it used plus and minus deltas, then we'd have a more accurate time difference as well as a space difference. The second derivative space was accurate enough. Okay? So the problem is, how do you get going then when all you know is one row at time 0? If we knew what the solution was at an earlier time as well, then we could use that to move ahead and have a forward difference method. Okay, so it's a method which uses, not just here, but in many places, this method known as a split time step. So we may have our time step as delta t each time on the lattice, but we actually will find the solution at a time in between. So let me show you what that means. So we'll evaluate this derivative, the time derivative, not at time t and time t plus delta t, but we'll be evaluating it at times t plus delta t over 2. So we'll evaluate it in the middle of a space based on the values on the lattice. So when we're done, we'll still calculate the lattice values, but the actual values of where the function might be calculated for the equation will be someplace in between. So let's do it, and then you can get an idea. So if we look here and say, okay, here we have the time derivative of the temperature at time t plus delta t over 2. What is that? Well, we can write that as a central difference method by saying, okay, let's take step delta t over 2. So we move ahead step delta t over 2. So if we add delta t over 2 to t at delta t over 2, we get delta t. If we subtract delta t over 2 from this time, we get minus t. So we have equation 1 can be thought of as either a bad approximation for using the forward difference method for the derivative at time t plus delta t, or as a good approximation using the central difference method at time halfway in between, at a half step. So we'll use this formula, but we'll evaluate it at time in the middle of the interval. So we'll actually be solving at the middle of the interval in terms of the grid values, and then we can get a much more accurate solution. Okay, so let's go through that. The only complication is we have our space derivative, second derivative. So again, we need to evaluate that someplace at half step. So we do that here on equation 2. And it takes 3 lines. That says enough, doesn't it? Okay, it's a lot of equation, but it's pretty simple. It's just the space now is minus delta x over 2 plus delta x over 2, then minus 2 delta x. So we have that, and then we have it's a combination equation 1 for the second derivative as well. Then we have the time here and the space minus and plus. So that is the second derivative. And now if we put the pieces together, we get a version of the heat equation in a discrete form at half the time step. Okay? So that's what we have here. So let's just go ahead and do that. So we have here our heat equation. Equation 3 is the heat equation. Okay? We have the first derivative now expressed in terms of the time differences, and now we'll express it in terms of values on the lattice. So we have that on the left-hand side. And then on the right-hand side, we have the second derivative, and a bunch of constants here, expressed in terms of lattice values. So it's the same equation, the heat equation, but it's being solved for times halfway between the steps. Okay? And then expressed in terms of the value on the lattice points at full time steps. So if you get that, the solutions will be the ones we want, although we're actually doing the approximation halfway in between, so it's a higher order approximation, but there are more terms involved. Okay? And can we solve this? Well, let's see. In order to solve it, we need to express an equation having only the future on one side and the present on the other. So we can rewrite the heat equation in finite difference form as equation 6 here. And if we look at it, we say, okay, remember the first index I is space, the second index, the j index, is time. J plus 1 is future. J plus 1 is future. J plus 1 is future. Okay. So the left-hand side of the red equation is all future. The right is present, present, present. We can do it. Okay. It's not as simple as before because it involves these three values, but it is an implicit solution. Okay. So why it's not as simple as implicitly, if we solve this equation, and it is of course not really one equation, I and j span all these values, and you have to write it down for all possible values, relate them all together to find the solution. So it's implicitly a linear equation. We can still solve it with matrix techniques. Fine. It is still a leapfrog method because what we say is, okay, we have to solve a whole bunch of algebraic equations at a single time corresponding to j. Once we have that, then we can use all these algebraic equations to step us ahead to get the solution at later time, j plus 1. Fine. Once we do that, we just reverse present and future and move ahead to a new future, one step at a time. So it's still time stepping, but we have implicit solutions at each step. So let's look about how we do that. Look at the next slide, please. Well, as with many things, until you actually do it, you don't know what the problems are, and you don't know how to do it best. So it's easy enough to say in theory it's possible. It's much harder to actually get a solution. So if you try to rearrange these equations, the neatest way to arrange them is to say, let's have all of the future on the left-hand side and the past on the right-hand side. So in this matrix equation, so this is now our implicit solution written down, doing what I said you have to do at some point in your life, writing it down as a matrix equation. These are the matrix equations you have to solve. So these are all the simultaneous linear equations for the temperature at all different points for one time only. We solve them for one time, then we move ahead. And what you see here is we've separated all the future, the j plus 1s on the left-hand side, but lo and behold, there's one future on the right-hand side. And that looks like it's a problem, but it's not a problem because this is the value of the temperature at a boundary condition. And since the boundaries are always kept fixed, temperature 0, we know this value into the future. So we got out of that one, okay? So we can handle it. So now that's what we have to do. Okay? So the right-hand sides are all, all known quantities. The left-hand side here are all unknown. We solve this as a matrix equation. It's our standard linear form, AX equals B. We can solve that. Okay. So we have here a solution. This is called the Crank-Nickelson method. It's actually more precise for the time derivative, so it gives us better solution, and it's also stable. In fact, if you work out the von Neumann stability analysis, recall, this is the analysis in which we express the temperature as an eigenmode, like a Fourier series with a plane wave, traveling wave, and an exponential dying time, and what we get is the amplitude of the eigenmode C of k is the wave vector, has this form. It's a good form because eta is a positive number, sine squared is positive definite, and so 1 minus 2 eta times sine squared is always less than 1 plus 2 eta times sine squared, so that the fraction is always less than 1. So the amplitude, regardless of what values you use for delta x or delta t, will always be less than 1. The method's always stable. It always converges. Okay? So it's a very stable method. It's a very good method, but we have a matrix equation to solve. If we go back and look at that matrix equation, and I'll go back and do it here, it has a very interesting form. Look at this matrix equation. We have here, along the diagonal, we have values. So that's the diagonal. It goes, And then we have another row of values above the diagonal and a second row of values below, but every place else we have big fat zeros. So this is a form of a matrix known as a tri-diagonal matrix for that reason, because it has 3 diagonals and everything else is 0. And there's no, it's not a crime to use our standard linear algebra techniques for this. It's just a waste of time and accuracy because there are special matrix techniques for tri-diagonal matrices, and they're fast and more accurate. So let's talk about that. How do you solve a tri-diagonal matrix equation? Well, there's 2 things you can do. One, you can ignore it and then just say it's still a linear equation. You've told us last course about these matrix algebra libraries. Why don't you just use the library and it works? Why fight it? Well, okay. Some of us, find the methods interesting and maybe you want to get a job and show off how fast and accurate you can do it. So we'll use a tri-diagonal method. And the tri-diagonal method, you could just look in the matrix library, and sometimes they have special techniques for the tri-diagonal method. And you could just use that. So this is optional now. This is what those techniques have to do. It's sort of interesting, and there's no real magic here. Okay? So we could use the standard linear algebra technique. This is the standard form of linear algebra. A, a known matrix, X, an unknown, B, a known. And we know the B values here. X's are the temperature at future times. And these are all known temperatures. And this is our matrix. Okay. So why do we want to do this? Well, the reason we want to change is if the matrix A is an ordinary matrix, it contains n squared words. And for each word in the matrix, you have that's how it scales, where n is the dimension of the matrix. You have a large number of accesses in memory. That's what slows you down. Okay? If you have a tri-diagonal matrix, we really only have 3 vectors. One here in black, which got destroyed for a second. We'll do it again. One here in black. Another here in blue. And the third in red. Okay? Those are the only elements, and those are just 3 vectors. They're just 3 lines, so there's only really 3n elements, or 3n minus 2 because the n's are truncated. So this scales as the problem gets bigger and bigger, like n, and the other one scales like n squared. And that could be a big difference. It can be hundreds of thousands. It could be the difference between getting the solution to a problem while you're watching it or coming back the next day or the next week. So it does matter, okay? So how do we actually solve this? Well, it's essentially the same way you would solve any simultaneous equation. You reduce it to a form where you can just solve each variable completely by itself. Here you do that by reducing the tri-diagonal matrix to one in which all the diagonals are 1. And when you have all the diagonals 1, you can just write down what the solution is. And so there's 3 steps here. It's just algebra. You divide the first equation by d1, then you subtract a2 times the second equation, and then we're left with this form. So you see here we have a 1 here. That's good. We have some elements here. That's fine. And now we have to, now let's say, what do we have to do to reduce the next diagonal element to 1? Well, you divide the second equation by that element, and then we're left with this equation. So now we have a 1 here, a 1 here. We have an off-diagonal element there, and this is that off-diagonal element. And now we do the same thing. Divide the third equation by the coefficient, and you go ahead. So when we're done, we're left with a tri-diagonal form, and then on the bottom here, you have an explicit solution. X's these are just the elements of that matrix. So you don't even have to invert a matrix. You just know what the solution is. And this division goes very fast. So in practice, it turns out that this leapfrog method with the tri-diagonal is as fast or faster than the ordinary leapfrog method, because it gives you the whole row of solutions in one fell swoop at any one time, and it does it very quickly. So it's not at all a bad method. So we give you a code, a sample code. Here we'll look at the sample Python code, and it's the same thing as we always talk about. There's a lot of setup, but if you go to the heart of it, what do you see? You see two interesting things. You see here a function being defined, which is the tri-diagonal matrix. So this is our own method. We wrote it up here rather than using a library, how you solve a tri-diagonal matrix equation, or set of linear equations with a tri-diagonal matrix, because it's so simple. And what you see is it's just like what we said. We do the reduction here, we do the divisions, and then at the end we just have the solutions here. The x's are just, again, the p minus explicit solutions. Okay, so and the rest is pretty straightforward. So that's the exercise. Go ahead and and try it yourself. Try the same kind of problems. Try new heat flow problems. We're just solving linear equations. You can use our code, or you can use the library. Always good to see how the library works. Check for stability. This should be stable for all values of delta x and delta t that you can figure out. Certainly for all delta t values, because that's all that enters the stability analysis. Again, do a contour plot, and then compare the speed of this improved time-stepping method, the Crank-Nickelson method, to the previous method for the same level of precision. Okay, and you could assume for those purposes that if you calculate something for a very small time step, that it's accurate. So make that comparison, and you've learned a more powerful method. And even if you don't learn the method, you've learned that this is how you go about improving things for when you have a job or when you have a research problem and you need better solution. It's not that hard, is it? See you next time. Bye-bye.